Hello guys, welcome to a brand new video of Q programming. Today, as you can see, we'll be talking about encoding schemes and number systems, which is the second chapter of the CBSE syllabus. So now, what are the main topics we're actually going to cover in this? Firstly, we're going to talk about the different kind of encoding systems such as Ascii, and Unicode. You guys might have heard of these somewhere or the other. These are the different, we're going to talk about this shortly. Then we have the types of number systems, which we're going to discuss right after that. And then finally, we're going to come to conversions between numbers. How do you convert from one to the other? So all these three are just three main topics that we are actually going to have, but each of these are very vast individually. So you guys will now see as we move through the chapter. So
before we get into the different encoding schemes, we need to talk about what encoding actually is. So encoding is the mechanism of converting data into an equivalent cipher using a specific code. What does that exactly mean? Basically, let's say I have a piece of data right here, and I want to input that into my computer. So my keyboard will convert that into a specific code, right? So let's the code be X. And then this code will be further converted into binary, which the computer understands, right? So let's make the binary random 10, 0, 1, 0, whatever, right? So X is our data in the encoded scheme, and this is our binary equivalent, and this is our original data, right? And now let's say my friend wants to take this. So what happens is his computer receives this data right here, and then he gets that. It's converted into this right here. And then finally, we get the original piece of data on the screen. And so that's basically how encoding schemes actually work. Let me just read that. So now, when we have a system like this, we have to make sure that it's uniform for all keyboards, right? Because if I have one encoding scheme and my friend has a different encoding scheme, then problems can arise because one thing I might put into the encoding scheme might be different for him, right? So let's say I type X and he ends up getting Y. That'll become very problematic, right? Because then we can't really do anything. So that's why many people have tried to create uniform encoding schemes, right? Standard encoding schemes, so that there's uniformity across computers, right? So let's talk about the three main ones that we have. The first one we're going to talk about is ASCII, or the American Standard Code for Information Interchange. This is the most commonly used coding scheme and one of the first ever created. So it's a 7-bit code, and that means there are 128 total possible values for ASCII. That means we can have 128 different characters. So after that, it's only applicable to the English character set, right? So this was created in the United States, and over there, the main language is English. It was developed basically to incorporate English characters, right? And not other characters. And then we have a few basic things here. So the capital A is number 65 in ASCII, and lowercase a is 97. So after that, we have the Indian script code for information interchange, which is called Ascii or something like that. And this is used to facilitate the use of Indian languages, right? Because in India, we have many different languages as well as different scripts, such as the Hindi script, the Urdu script, etc. So this is an 8-bit code. It has 256 characters, so 256 total possible characters in this encoding scheme. And it uses the first 128 ASCII values. So basically the 128 ASCII values that will be in this one over here in the top, those will be the first 128 for Ascii. And then after that, additional codes have been assigned for aksharas of different languages, right? So in addition to the English characters, we've got characters for various Indian languages as well. After that, we have Unicode. So now you see we have Ascii, but those are not the only encoding schemes that were created. There are many coding schemes created throughout the world, and because of that, there are many problems. If I want to send some data to a different country, but they do not follow the same coding scheme as I do, it'll become very problematic for me. And that's why Unicode was created, so that it could incorporate all the characters around the world. Basically, it incorporates all the encoding schemes that have been created to date. So it can be used on any device, operating system, or software. So most of the software these days is based on Unicode. And it's a superset of ASCII again. And the first 128 values have the same characters as ASCII. and it's basically encoded in hex values, which we'll just come back into in a few minutes. It's one part of the number systems. Yeah. So now we'll just move on to different number schemes in detail.
So now we have printed an Ascii table up here. So we're just going to see how one is supposed to read this, right? So what does an Ascii table contain of? It contains of the decimal values of each character in input in a computer. Now you will actually see that all of these symbols, this exclamation mark, double quotes, stars, dollar sign, etc., all of these, like the numbers also, each have their own specific value, which you can see on the blue to the left, right? So this represents 32, and the one in red you will see is the hexadecimal value. We'll talk about what they are shortly. So now what you would want to keep in mind is that capital A is 65 and small a is 97. Now why you want to know this is because like the computer, now while you are trying to figure out what would be the Ascii value of some say word, you won't actually, like, if you don't have this table with you, what will you do? If you know that capital A is 65, you know that it goes in increasing order, so you can just find out the Ascii value of any letter that you would actually want. Same for the small letters, and the rest of them, the special characters such as exclamation mark, space, etc., have their own unique values, and the computer converts it all into a readable form, which is then printed on your screen. So like we talked, it has a 7-bit representation. So let me give you an example of how you're supposed to read this table. So if I have this question to convert the word hot, capital HOTS, into decimal form in Ascii value, so what will you do? You will first find each and every word and you will write them together. It's very easy in that sense. So what would capital H be? Let's look at the table and find out. So capital H is 72. These two, 72 and 79. So the first two are 72 and 29. And then we need capital T and capital S, which is going to be there. Our capital T would be so capital T would be 84 and capital S would be 80. So 84 and 80 is 80. So now what I have actually done is, I'm so sorry. What I've done is I've just converted it into decimal form. Now what the computer does is it converts this number you see in front of you into binary, and we're going to talk about how the computer does that in a while, and we're going to give you some numericals to practice as well. So this is how the computer actually goes about. Now
Okay, so here we have the Indian script, which is in Unicode, right? And you can see that by the U plus. So can you zoom in on that? So here we have different values. So you see we have U plus 0900, U plus 0901, and this is all in Unicode, right? So basically this is in hex values. And then the computer will basically be converting hex to binary. We'll also be showing you how to do that manually. It's just a little bit how to actually go about when you look at these. It looks very complicated, but it's actually quite simple when you understand how it works. And since the computer is very fast, it can do all these calculations very quickly, but we obviously can't. So that works in our favor.
Yeah, exactly. So now we're gonna get a look into how the computer ends up doing this conversion. Like, what are the processes that go into it? So for that, we need to understand what are the different kinds of systems. All of you, I'm sure, have heard the decimal number system. It's the number system you use all your life. 1, 2, 5, 6, 1. And there are 3 number systems we're going to use this time.
Yeah, so besides decimal, there are different number systems we'll be looking at right now. So let's talk about two key terms we use while talking about different number systems. The first one is called radix. And radix is basically the base of the system, i.e. the number of elements we can get, right? So let's say decimal, we have 10 available elements to us. That's 10. That's our radix, right? And the elements available are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? These are the different digits we have in our decimal system. And that's what comprises of the decimal system. And basically the decimal system, we'll be looking at that, which is, let's look at the first 15 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, those are the first 50 numbers in our decimal system. Let's look at binary. So binary has basically a base of 2. So the radix is 2. And the digits available to us are 0 and 1. Now there's a cool little trick you can use while writing the first 15 elements of binary. And it works for even greater numbers, but we'll do it for the first 15. So we're going to look at the different places we have, right? So we have 1, 2, 3, 4, right? And then 0 will be 4 zeros. 1 will be this. And then 2 will be this. And then 3 will be this, right? So there's a small pattern you can see here. In the first column, the 1 column, it's alternating between 0 and 1s, right? So we get 0, 1, 0, 1. So we'll continue 0, 1, 0, 1, 0, 1, right? Here it's alternating between 0 and 1s every 2 elements, right? So 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. And then after that, in the third column, we'll actually be alternating between every 4 elements. We have 4 zeros here, now we'll have 4 1s, 2, 3, 4, then another 4 zeros. Then after that, let me just continue this down. So we have 0, 1, 0, 1, 1s, 1, zeros, 0, 0, 1, 1. In the fourth column, we have for every 8, is alternating every 8 cycles. 2, 3, 4. Then we have 1, 2, 3, 4, 5, 6, 7, 8. Here we have 1, 2, 1. Right, so it's a bit messy here, but we will provide a better table on our website in the notes. Don't worry about that. Let's talk about octal. So octal, as the name suggests, has 8 elements. So our radix will be 8. Right? And what is available to us? We have 0, 1, 2, 3, 4, 5, 6, and 7. These are the digits available to us in the octal number system. So let's look at the system. So we have 0, 0, 1, 2, 3, 4, 5, 6, 7. And then after that, we will start from 1, 0, 1, 1, 1, 2, 1, 3, then 1, 4, 1, 5, 1, 5, 1, 6, 1, 7, then again 2, 0. It looks a bit confusing, right? We go from 17 to 20, but keep in mind this is the octal system. So while you're doing this, after that we have hexadecimal, and hexadecimal is basically for 16. So we have 16 here, and we have 0 to 9. That's the first thing. And after that we have A, B, C, D, E, and F. So these are 16 literals we have, basically the elements, right? So you have the first 10 digits of the decimal system plus A, B, C, D, E, F, right? Let's look at the first 15 elements. So it'll be 0, 1, 2, 3, 4, 5, 6, 8, 9, A, B, C, D, E, F. So the first 15 numbers, first 16 elements of our hexadecimal system.
Okay, so one thing you should keep in mind is that capital A actually represents the value of 10. And when you actually go into calculation, I'll tell you why that will actually come in handy. So this is how the 4 numbers that we're going to talk about today actually work. And now we're going to discuss methods through which you can convert between one another. Like for example, you want to know what is 0110. How will I know what is that in my decimal? What is that in octal? What is that in hexadecimal? Because the computer uses all of these number systems together. So there has to be some uniform method of conversion between them, and discuss them with examples. So the first we have here. Okay, so now I would recommend you, because I have given like 2 questions. So I would want you to first I would first explain you how to solve the first question. Then I would like you to pause the video and try the second one yourself, right? And we keep going on like that. Okay.
Yeah, so just before we start this, we're going to discuss one quick concept. It's called a position-based number system. That's very key factor in doing these conversions, because without it, you won't be able to understand. So let's look at a number. Let's say right here. Just write that. We have 1, 2, 4.05 in decimal, right? So what are the positions for us? So we don't count the decimal as a position. So this is no position. Okay. And then the 4 is at the 0 position, 2 is at 1 position, and our 1 is at the second position, right? And here we have -1 and then -2. So basically, the number just to the left of the decimal point is your 0. And then after that, it goes increasing order. And to the right of that, it goes decreasing order. It's just a little basic thing you must know while doing these conversions.
So, okay, so now we're going to talk about how to convert between other number systems to decimal. So like Samar just explained, if now I'm just going to take an example of this binary number right here, right? We have the decimal point. So now, like the thing says, you would want to take the power of the index values of the digits and add it. I mean, like you have to add all of them together. So I'll tell you what that means. So firstly, like I'm just going to quickly go through this. What are the indexes of each of the numbers here? So now this, like someone said, would be 0. Then this would be 1, that would be 2, and so on. And this 0 will be -1, -2, and like that. Yeah. So now you guys know how to write the indexes. Now we're going to talk about some examples. So like the thing says, you have to take the base to the power of the index value. What does that mean? Like now we are talking first you're going to do binary to decimal. So what is the base of binary? 2, right? So you would want to take the index to the power of the base and add everything together. And if the indexes have negative values, you take it to the negative power. We're going to discuss an example. Like right here, if you have 1, 1, 0, 1, 1, 0, 0, 1. If we want to know the decimal equivalent of it, now what I will do is I will say, okay, so this is at index 0. So 1 is to the power 1, right? Then you would do Great. So now since we have 1 over here, I'll do 1 multiplied by 2 to the power 1. Then I'm going to add 0 into 2 to the power, that'll be 2 to the power 0. Then I'll do 0 into 2 to the 1 plus 0 into 2 square Now we've reached index 2. Now index 3 has a value of 1. So plus 1 into 2 to the power 3 plus 1 into 2 to the power 4, because the fourth index also has 1, plus 0 into 2 to the power 5. And you just keep going on like this. 0 to the power 5. 1 into 2 to the power 6 plus 1 into 2 to the power 7, right? Plus 1 into 2 to the 6 plus 1 into 2 to the 7. Now all of you, I'm sure, are very familiar with the powers of 2. So we're just going to ignore the 0 terms and we're going to solve for this expression that we've derived over here. So this will be 2 plus, so this is 0, that's 8, that's 16, 2 to the power 4, then 2 to the power 5 is multiplied by 0, so we do not consider that, then 64, then 128. So if we add all of this up together, the final thing we get is 10, 26. So 20, I'm just going to write it in steps, 26 plus 192, and we finally get 8, 20. So that is the equivalent of our binary number that we were looking for. Okay, so this is for the first one. This thing you'll notice that there's a decimal point around here. So like I told you guys, decimal point behind the indexes. So just as the rules here, take the powers. So first we'll do the positive powers. That's 2 to the power 0 plus 2 to the power 1 into 1. I'm writing down. Want to know more questions? You can not do 1, then just keep doing the 1s. Plus 2 square into 1. And plus 2 cube into 1. So that's for whatever's on the right of the decimal. Cube into 0. Similarly, now if I add this, this will become 2 plus 5, 6. That will become 6. On the other hand, behind the decimal, we say 2 to the power minus 1 into 1 plus 2 to the power minus 2 into 0 plus 2 to the power minus 3 into 1. And since now we know that 2 to the power minus 1 is 0.5 and 2 to the power minus 3 is 0.125. So we'll get 0.625 behind the decimal on the other side. So hence our final number, the decimal equivalent of that is 6.625, and that is our final answer. Okay, so that was the first and second part. Okay, now we'll, like, this is the process you have to repeat for any number system when you have to convert it to decimal. Let's talk about octal to decimal.
Yeah, so octal to decimal will follow the same procedure, and here our base will become 8, right? So we talked about it in the table before. Binary was 2, so octal is 8. So basically, let's start with 235, right? So we have 235 base 8. And we want to convert it to its binary decimal equivalent, right? So what we're going to start is we're going to start with 5. So its index is 0. So that means we have 5 times 8 to the power 0. Then we have add right here 3 is at the first index. So we have 3 times 8 to the power 1, and then after that we have 2 at the second index. So we have 2 times 8 to the power 2. So let's just calculate this. So 8 to the power 0 is 1. So we have 5 plus 3 times 8, 24, plus 2 times 8 to the power 2, so 2 times 64, plus 120.
That'll be 18.
Uh,
18 over.
Oh, sorry, yeah.
18,
Sorry.
Exactly.
3 times 18. And then when we add all these, we get 23 plus 128 is equal to 151. So that's the equivalent in decimal.
So you might be noticing these numbers he's putting like in the script of the number. This is actually to denote what number system we're talking about. Like here, if I was converting a decimal, I should have written it this way. I brackets around it and I write 10. Same for that. So now initially converting from 3, so like this base indicates what number system we're actually talking about. 10 would be binary, 2 would be what am I saying? 10 would be decimal, 2 would be binary, 8 would be octal, and 16 would be hexadecimal. Right?
Yeah. So now let's look at the second example. So here we have 241.2 in octal. So let's start. We will put a decimal here, and let's start from the left hand side. So let's start with index 0. So it's 1 times 8 to the power 0. Then index 2, index 1 we have 4. So we get plus 4 times 6 to the power 1. And then at the second index we have 2. So we get 2 times 8 squared.
So that we 8.
So we have 1 plus 24 plus
And it will
120.
be 8, 32.
So this is our left hand side. On the right hand side we have 0.2, right? So just go up here. So 0.2 times 8 to the power minus 1. That's basically, that's 2 times 8 to the power minus 1 is basically equal to 1 by 4 is equal to 0.25. So now if we join both these right here, we get 161.25.
Right. Okay. So this is how we convert from octal to decimal. Now we're going to take one more example, which is hexadecimal to decimal. So now the number you can see is 3A9. Now I told you guys before that when you guys consider this, A denotes capital 10. But okay, that's not really going to be very helpful right now, but it is actually. I'll tell you how. So if you have 3A9, right? So this denotes index 0. this denotes index 1 and that denotes index 2. Right now I'm just writing on the indexes, nothing else. Now since we know that our base is 16, I will just do the math. So what is be 6 to the power 0 to 9 plus, now a we will consider 10 because we can't actually say a into 16 to the power 1, that would make sense. So we say 10 into a to the power 1, 10 into 16 to the power 1, and we'll add it to 16 square. Right? So now we just do math. This will be 16 by 0 is 1, so it will be 9 plus 160 plus
3 times 56.
yeah. So I just have to do the calculations here. Now as you guys can see, these calculations are lengthy, but this is actually how, these are the kind of things you will have to solve eventually while learning this. So we'll just solve this quickly. We get 16 plus okay, so he solved it for us.
So I used to calculate it here, but you won't be allowed to do that in the exam.
Yeah,
so just make sure you practice with your speed.
Yeah, and then that is equal to 937. Okay, so this is how this is how the example I gave. Now we're going to discuss the second example. Yeah, right. Okay, so now in the second example, okay, good. Now last example, we have 2b.4c. Now first thing we want to do is write the indexes of all of them, so we'll just quickly do that. B point, that's not an A, that's a B. 4c, that'll be index 0, index 1, index -1, and index -2. Okay, so this will actually give a very long value a to the power -2. So we'll first have so what is the value of b? We know that, right? So b would be so since a is 10, so what will b be? 11, right? So 11 into 16 to the power 0 plus 2 into 10 to the power 1. Now these calculations are always very hectic because there are such big values you need to deal with. So that will come 11 plus 32, and that is 43. So now we know what's on one side of the decimal. Let's find out what's on the other side, right? So now let's consider this. So first we'll have 4 to 16 to the power -1 plus, now with 13 into 16 to the power -2. So that will be 4 by 16. So if you like do it 4 by 16, 1 by 4, so 0.25. And this will be 0.25 also, 0.125 into 13. So So sorry for that. So we have so calculation, but it's okay. I solved it. And if we solve this, like you guys did, that's actually more important than doing the whole thing. So it's 0.165. 50, but we don't have to consider that since it doesn't matter. So finally, our answer would be 43.165. So that is our final answer. Yes. Okay. Now we're going to talk about a rather easier conversion, because you can see this conversion is a little hectic. Now in the next one, you just have to divide. It's much easier than multiplying everything. So sorry. Okay.
Yeah. So let's the easiest way to actually explain this is through an example. So we'll start with a decimal to binary conversion. So the first one is 43. So we have to convert 43 into zeros and ones, right? So what we're going to do is we're going to make this 43. And then what we do is we're going to divide by 2. So we divide by 2. And then what we get is 2 times 21 is equal to 42. We divide by 2, we get 21 and a remainder of 1. And we divide this again. We get 10 and a remainder of 1. Divide again. 5, 0. Then we divide again. 2, 2, 1. Then divide again, we get 2. Then we get 1, 0. Divide by 2, we get 0. Down. We get 0 and 1. So what we're going to do is, we're going to ignore all this stuff here, just cancel that out for now. And we'll focus on this part here. Right? So what we're going to do is we're going to write it from bottom to top. So we get 1, 0, 1, 0, 1, 1. And that's what our number will be. So we can also quickly verify. So 1 times 2 to the power 0 is 1. Or 1 times 2 to the power 1 is 2. 0. 1 times 2 to the power 3 is 8. 0. 1 times 2 to the power 5 is 32. So what do we get here? 32 plus 8 plus 2 plus 1, so we go to 43. So this is our final answer in binary.
So like when the computer gets any number, I mean any letter which suppose has the index 43, this is how it actually converts it.
Yeah. So now let's look at an example with decimals. So this is a fairly easy example when we're using only integers. So in decimal, we're going to first start by converting the natural number part. So what we're going to do is we have 23. So we have 23 right here. Beneath that table again. So we're going to start with 2. We get 11 and 1. 2, 5, 1, 2, 2, 1, 2, 1, 0, 2, 0, and 1, right? So now we write this here, we have 1, 0, 1, 1, 1. And then we put a decimal point here for the next part. Okay, so after that, what we're going to do is, we have 0.45, right? So what we're going to do is we're going to keep multiplying by 2 until we get a 0. So we get 0.45 times 2, which is equal to 0.9, right? So let's write a 0 here. So we're going to take this value over here. So it is 0. We're going to take 0.9 right here. So we get 0.9 times 2 equal to 1.8. We take a 1 here. Then we have take this 8.8 here. We have 0.8 times 2 equal to 1.6. Add another 1. We get 0.6 times 2 equal to 1.2. Another 1. We get 0.2 times 4 times 2 equal to 0.4. We add 0. After that, we get 0.4 times 2 equal to 0.8, which is equal to 0. Yeah, so it's going to keep repeating itself. Yeah. So what we're going to do is we're just going to simply keep the first set before it repeats. So we have, first we got 1 0 1 1 as 23, and to that we'll be adding 0.0 1 1 1 0 0.
Okay, so now that is an example. Now see, you don't actually have to multiply all the way till here. You just have to take the first 4 values. And like the first 4 values are more than sufficient to give your answer. But now we're going to talk about octal. Now the method is the same. The only thing here is now we have to keep dividing by 8, right? Because for in binary we are dividing by 2, here we have to divide by 8. So 25 in binary. Now, like we discussed above, you just have to keep dividing and read the remainder bottom to top. So now 25, this is a fairly easy example. You just divide by 8, you get 8 3s are 24, so you get a remainder of 1. Then you divide by 8 again, and you get 0 and 3. So this is a fairly easy example. You just read bottom to top. And
okay, in the second part we have 40.2. So let's divide 40 with 40, 8, 5. So we get a remainder of 0 here. When we divide by 8 again, we get 0 and a remainder of 5. So before the decimal we have 50. Now let's look at the part after the decimal, right? We have 0.2. So what we're going to do is we're going to multiply 0.2 by 8 until we reach a 0. So 0.2 times 8 is equal to 1.6. So we're going to note this value here. So we get 1. Then we have 0.6 times 8 is equal to 4.8. We get note 4. After that, we're going to take 0.8 times 8 equal to 6.4. And we take 6. Then we have 0.4 times 8 equal to 3.2, which is equal to, we get 3 here. We take 0.2, and then we're going to have a loop here, right? So let's keep repeating and repeating and repeating. It will be non-terminating. So we just take these 4 values here. So we get 0.1463. This is an approximate value. And then this is a value in decimal. This is an approximate value, not the exact, but as close as we could get. So now let's move on to decimal to hexadecimal. So we'll follow the same procedure, except this time we'll be dividing by 16. So let's start. So we have 67. So we divide by 16. So we get 4 and a 3 as a remainder. Now we divide by 16. We get 0 and 4 as a remainder. So the answer is 43 in hexadecimal. Now, let's move on to 51.2. So this is decimal, hexadecimal. Okay, so 51.2. Let's start with 51. we have 51, 16, 3, and 3. 48 plus 3 is 51. Divided by 16 again, and we get a 3, right? So the part before the decimal is 33. Then after that, we have 0.2, right? So what we're going to do is we're going to follow the same procedure again. So 0.2, shift to the right a bit. 0.2 times 16, which is equal to 3.2. And we're going to put 3 here. Take the 0.2 again, times 16, equal to 3.2. So now as you can see, it's going to be an infinite loop. So the answer will actually come out to be 33.33 bar. Or it would be 33.3 bar, right? Or whatever. So that's basically all the conversions from decimal to other number systems. And now we're going to look at the easiest part of this chapter, which is octal to binary and hex to binary. That's one of the easiest parts you can have. And what we're going to do for this is we're going to make a table. So I'm going to copy paste the table I've made here. So I'm going to add these to the notes that you're going to get. So we're going to use this table to actually help us. So I told you in the beginning how to actually write all first 15 binary numbers and then the respective hex and octal. So this becomes very, very helpful to us when we're doing all this because it's like a cheat sheet and it just makes things very fast. So what we're going to do is, let's start with the first example. We have octal to binary, right? So what we're going to do is we have 204 in octal. Okay, we have 204. So what we're going to do is we're going to split each component into the respective binary part. So 4, 0, and 2 will find the binary value from this table over here and then write those. So we have 4. If we look at 4, binary value is 0, 0, 1, 0, 0. 0 is 0, so we add 3 zeros. Wait. Small mistake here. Yeah. So we have 0, we have 100, then 0 is 0, 000. And then 2 is 0, 1, 0. You can ignore the first 0. And we have 1, 0, right? So we're going to use 3 places. Yeah. And then we have the next one, which is 1, 4, 2 in binary, 5 and 2 in binary. So we take 5. 5 is 101. 4 is 100. 0 and 1 is 001. We can ignore the first 2 zeros. So we get 1. And then after decimal, we do the same thing. And we have 2, which is 0, 0, 1. Yeah, 0, 1, 0, sorry. Yeah, 0, 1, 0. Okay, so that's how we convert octal binary. And now let's do the hexadecimal to binary.
Yeah, okay. So in this, like in octal, we actually consider 3-bit places. In hex, we consider 4 bits. So now what we're gonna do is, like you can see that we're trying to the 8 elements, like we talked about it. So we have 7D5. Okay. Now you will first want to see what is. So I'm just gonna refer back to this table. So this is 0,111. So I'm just gonna write it. It is 0,111. Then I'm gonna see what D is. Okay, so we can see D is 1101. And 5 would be 0101. Okay. So this is our hexadecimal which we just right? Now we do this one, 64.2. Now you just have to keep the same procedure. So 6 will be 0, 110, 110. 4 will be 0, 0, 0. And E will be, I mean, E is the second last, so I'm just going to use this one, 1, 1, 1, 0. And 2 is 0, 0, 1, 0. So now this number that you see in front of you is the binary conversion of Ascii. Okay. Okay. So that's my value here. Okay, so now if we go from octal to decimal or the other way around, we're gonna have to convert it to binary and then convert binary into that's it. So now we'll see what binary to hexadecimal. This is the reverse process of what we just did. So first you wanna see what are they asking. Now this question asks for octal. So firstly, we're going to break it into 3 bits. So this comes here, then 3 more bits here. And then you check the octal value of each of these individuals, right? So now, what is 110? I'll just zoom out and see the table. Okay, I have the table open in front of me. So, 110 is 6. So 6. Then 0, 2. And 0, 1 is 3. 23 is the representation of this. So now instead of actually going through all of that, first converting in decimal, then doing this, you can just directly do this. This is a much easier method to convert. You just have to refer to the table we showed.
Yeah. So now we're going to look at 11001.101. So let's break it into 3 first. Here's zoom in a bit. So we break it into 3 here and here. Right, and we can add zeros before and after. Right? So let's look at before the decimal. 001 is 1 and 011 is our 3. Right? And 010, that would be 2. So we get 31.2. It's very simple. This is one of the easiest ways to do it. And after that, we have hexadecimal. So we'll be breaking into 4 groups, right? For octal, we do 3, and for hexadecimal, we do 4. Just remember that. So let's going to break it into 4 first. 4 and 4, right? So let's start. Here's a decimal. 1001. I will refer to my table that I have here. In hexadecimal, that's 9. So you write 9. Okay. After that, we have 1101. So in the table I have here, 1101 is a D. So we have D9. And then over here we have 0001, which is a 1. So we get D9.1.
And you can see they are actually broken into 2 pieces for us. So from the decimal point, first create groups of 1, 2, 3, 4, we create 1 here. And 1, 2, 3, 4, we create 1 here. Sorry. So 1, 2, 3, 4. Now that comes down. Okay, so now, like we said, on this side of the decimal, you can add as many zeros as you want. So I'm just going to add 3. so that we have a 4-bit representation, and I'm just gonna add 1 here. Okay. So now, according to the table I have in front of me, 0, 1 is so 0, 0, 1, 1 is 3. 1, 0, 0 is 8. Pointer. 0, 1, 1 is 1, and 0, 1, 1, 1 would be 7. So 71.38 is the value of this binary. So as you guys can see, this is much easier than the rest versions. This doesn't involve any physical calculation. You just have to refer to the table, break it into bits, and write the.
Yeah.
Now,
so
last one.
yeah. So last one is octal to hexadecimal and vice versa. So this is a 2-step process. So first we're going to convert 34.6. So 34.6 is in octal, and we're going to convert that to hexadecimal, right? So what we're going to do is we're going to break up the octal into binary, right? Same way we did before. So we got on the decimal point here, to the right, we have 6. So 6 in binary is 0, 1, 1. Here, 0, 1, 1. 4, which on the left of decimal, is 1, 0, 0. And before that, we have 3, which is 0, 1, 1. You can just write it 1, 1. Right? So now what we're going to do is we're going to convert this into hexadecimal.
In 4 bits.
Yeah. So what we're going to do is we're going to add zeros here and zeros here, because 0 won't have any impact. And we're going to break this into 4 chunks. Here and here, right? So now 1100, 1100 is C. So we get our C here, and 0001 is 1, 1C, and then our decimal point here we have 0, 110, which is 6. So we get 1C.6. This is a fairly easy process, just 2 steps.
Right. And if we have 92. Now, firstly, you want to convert this into binary, which is an octal one. So, what will we do? First, we'll do B. So, what is B? Now, that is 1011. So, we just write that, and we put the decimal point. Okay. Then we have 2. So, 2 is 0010. Now you guys can see that this is fairly easy, but it doesn't make, because you just imagine 1 and 0, then there's a very high chance you interchange them. Like, it happens. So the only thing you do to minimize that is practice. And the 9th one is, and then 9 is 1001. 1001. Okay. So now from the decimal point, you want to make 3-bit representation. So you do this, you do this, you add a 0 here so that you get a 3-bit number, and on this side you just put 1 and 2 zeros. So now we will refer to the table again. So 100 will give 4, 101 will give 5, 0.110 will give 2, 0 and 0 again will give 2. Okay, so that's 222.4. And that is the representation of 2.B. So these are all the conversions. We are done with the conversions.
Yeah, so that's basically the end. Now, one thing before we go, why do we use different number systems? Why can't we just use decimal? Well, in the next video we have, based on Boolean algebra, we'll discuss why we use Boolean mainly as the language for computers. But otherwise, why do we use hexadecimal? So hexadecimal has 16 characters in the system, and it actually makes it easier to memorize and address. So we can have a long string of binary for data, but hexadecimal can reduce that actually. So if you have, let's say, 16 binary characters, hexadecimal can be done in 4, right? So that just makes it much easier to memorize data. And besides that, it can be used on a much bigger scale. So some examples of hexadecimal include when we choose color codes, right? So if you've ever seen before, we use hashtags for color codes. So you have 6 places. So you have basically 255 color values ranging from 0 to 255. It's also known as RGB format. So what you do is you actually write color codes in RGB formats. Basically, you have hashtag R G G B B, and then you put hex values here to basically specify what your colors are. So, for example, our website, the background color there is hashtag 6 3s, right? So basically, this is the RGB value for our website background color. So many different applications of hexadecimal, and it just becomes much easier to memorize. So when I'm actually working on the website, instead of actually having to memorize the binary equivalent, I can just memorize, oh, it's 6 threes. This makes it much easier.
Right. And now, as I've seen, this chapter is very heavy articles, and we have just shown examples so that you understand how to solve it. We want you to solve these questions by yourself, and as you can see, we typed down all the questions. So if you can go back to the video, pause, and try these questions by yourself. And nothing can replace hard work. The ball is in your court. Best of luck.
Yeah, we'll be uploading some of our cheat sheets to the website to make it easier for you. And we taught you the trick how to make the table. So when you're taking a test, just quickly make the tables. It'll become much easier for you to solve these questions instead of actually memorizing the values, because there's no point in memorizing all these values when it's easy to make the table. You can learn it in less than a minute. So that's the end of the video. Thank you for watching. This was a quite a long video, but it's a very numerical based chapter. So a lot of practice is required when you're doing this chapter. So just keep practicing this. It's not very theoretical, which is great. Numerical, very practical based. So once you've understood the concept, it's actually very easy to apply, and you can just do all these questions with ease. So thank you for watching. Please subscribe to our channel, like the video. We'll be posting some links in the description for our website where you can get notes, and also our Instagram where you'll be finding a lot of daily content. So thank you for watching, and stay tuned for the next video.
Yes. Bye.